Hey Calc friends, welcome to section 4.8, Newton's method, also known as Newton-Raphson's method. What it is similar to linear approximations, and it helps us find roots. It's typically how root finders and computer programs work also. Remember, calculus was invented way long before calculators were, so we had to have other methods to find things like roots of equations before we had our calculators to do that stuff for us. So just a friendly reminder, if we're looking for the equation of a line tangent to a curve at a specific point, we need two things. We need to find the slope, right, at A. And we do that by finding the derivative of the function and plugging in A. And then we need a point. And the point, the input would be A, the output would be f of A, right? And then the equation of the line would be y minus the y value you know equals the slope times x minus the x value you know. And then just clean this up a little bit. We get y equals f of A, just bringing that over to the other side, plus f prime of A, x minus A. So this is the tangent line approximation, or the linear approximation of the function f of x at the point x equals A. It's also the equation of the line tangent to the curve at this point. They share that point. All right, so what are we going to do with this? Well, let's take a look at what's going on. So we have some function here, f of x. So this is my f of x. It's this curve right here, right? All right, our goal is to find that point right here. And it's not always a nice x-intercept. So we have to do some work often to find that. What we initially do is we let a1 be a guess to that value where it crosses the x-axis. So let's suppose a1 was my point right here. And I know it's a little bit off, but for the sake of demonstration, I had to keep it far enough away so we could see the picture. So if we find the equation of the line tangent to the curve, f of x at a1 right here, so that's this guy, right? The equation of the line tangent to the curve at that point is, well, the slope is the derivative at a1, right? And the point is a1 and the function evaluated at a1. So we put this all together and we get y is equal to f of a1 plus f prime of a1 x minus a1, right? That's the equation of this line right here. Now what we look for is where that tangent line crosses the x-axis. We find the x-intercept of this line, which is right here. So that's our point. That's going to, and we're going to use that point as our next tangent line. And we're going to find the tangent line at that point, but we're going to use that as the next approximation to where this function crosses the x-axis. So again, here's my function f of x right here. I pick an initial approximation. I estimate where I think this is going to cross the x-axis. We call that point a1. We find the equation of the line tangent to the function f at a1. And then we identify where that tangent line crosses the x-axis, and we're going to use that as our next guess at where this function crosses the x-axis, the original one, because remember, that's our goal right here. Let's make our goal nice and bright green right there, right? That's our goal right there. Notice where the tangent line crosses the x-axis is closer to our point of interest than one we started with. So we need to find the x-intercept of this line. Well, the x-intercept of that line is when y equals 0. So we're going to set y equal to 0 and solve for x. So if y equals 0, we get 0 equals f of a1 plus f prime of a1. What those will all be values we know once we know the function and we know that initial guess. Now we want to solve for x. So now we have to do the algebra here. We're going to solve, we're going to find the value where that tangent line crosses the x-axis, the x-intercept. All right, so we are going to, let's subtract f of a1 first. So negative f of a1 is equal to f prime of a1 times x minus a1. Okay. And we're going to divide by f prime of a1. So negative f of a1 all over f prime of a1 equals x minus a1. Right, now all we need to do is solve for x. Let's just add a1 to both sides. So a1 minus f of a1 all over f prime of a1 and that's the x-intercept. So therefore, the x-intercept of this tangent line of y equals f of a1 plus f prime of a1, x minus a1 is x is equal to a1 minus f of a1 all over f prime of a1. Woo! Right, we're going to call this x-intercept a2 and then repeat the process. We'll use this x-intercept as our next approximation we'll call it A2. Right, so A2 is the x-intercept of the tangent line at A1. So now, here's A2. We're going to see where that point reaches the curve, and we're going to draw the tangent line at A2 right here. So the tangent line at A2 is this guy. And look where the tangent line, that second tangent line, crosses the x-axis. It's even closer than A2 was, and that's going to be A3. And then we're going to find the tangent line at A3, find where that tangent line crosses the x-axis, and use that as our fourth approximation. We're going to repeat this process over and over again until we get so close. So the tangent line, the equation of the line tangent to f of x at x equals a2 is y is equal to f of a2 plus f prime of a2, x minus a2, and its y-intercept, nope, its x-intercept, sorry, is x is equal to a2 minus f of a2 all over f prime of a2. We call this x-intercept a3. So a3 is going to be a2 minus f of a2 all over f prime of a2. And we continue this process over and over again. And the idea is these iterates will get closer and closer to the actual root of the function. Repeat over and over and over. Okay, and we get this template. The next intercept is the previous intercept minus the function evaluated at the previous intercept all over the derivative at the previous intercept. So this is going to be the template that's going to guide us to find a sequence of numbers that should converge, if we do it properly, to the zero of the function. So the limit as n goes to infinity of an is equal to r, where r is the root of the original function. All right, so let's try this. I think it's easier to see once we get this into play a little bit. Use Newton's method to approximate the root of 2x squared minus 6x minus 5. So we could just use the quadratic formula because this is a quadratic equation. We're looking for the root that falls between 3 and 5. So I'm going to actually graph this guy really quick. I'm going to do y equals 2x squared minus 6x minus 5. Let's see what this guy looks like. All right. So here's what this function looks like. And we're looking for the one right here, the one between 3 and 5. Okay, so we're looking for that root. It's not a nice whole number. I can see that it doesn't cross the x-axis in a nice place. Again, we could use the quadratic formula, but here we're just going to to attempt a first try at Newton's method. So the first thing we need is an initial guess. All right, so we're looking for a number between 3 and 5. When I look at my calculator, obviously in the old days we didn't have one, but it's somewhere between 3 and 5. So I'm going to guess, well, a good guess between 3 and 5 is 4. Not everybody has to guess 4. You could guess 3.5. You could guess, 4.9. It should lead you to the answer in the end. All right, so here we have our function f of x equals 2x squared minus 6x minus 5. The derivative is 4x minus 6. Right? So if a1 is equal to 4, that's my initial guess. A better guess should be this point minus the function evaluated at 4 all over the derivative evaluated at 4. So we have to put 4 in here. We have to put 4 in here. Okay. And when we do this, we get, I'm just going to write this out one time because it's going to get very messy very quick. F of 4 would be 2 times 4 squared minus 6 times 4 minus 5 all over 4 times 4 minus 6. And this does work out nicely. This is 4 minus 3/10, which is actually exactly equal to 3.7. So 3.7 should be closer to the true root of this function than 4. And then I'm going to repeat the process. I'm going to do the third iterate is going to be the previous one, 3.7, minus the function evaluated at 3.7, all over the derivative at 3.7. So we're going to do this, even though I said I wasn't going to do it, I'll do it one more time. Minus, let's see if I can squish it in here, 2 times 3.7 squared minus 6 times 3.7 minus 5, all over 4 times 3.7 minus 6. Whew. Now key is to use parentheses properly when we're doing this. The whole numerator has to go into parentheses and the whole denominator, right? And then fractions, you can use the division. So make sure you put all these, and you practice using your calculator now. And I did this, and it's not a nice number. Even when I tried to do the math fraction, it does not come out pretty. I get 3.679545455. Right, so we started at 4. We moved to 3.7, and then Newton says, no, a better approximation is 3.67. So notice that they're getting, the difference is smaller between the two numbers. And we're going to do this again. So now this is where it becomes insanely tedious, because now you have to take this number and you want to use as many digits as your calculator gives you. Your fourth iterate is going to be the third number minus the function evaluated at this third number all over the derivative at this third number, where this is A3. So you got to stick this number in here, you got to stick it in here, and you got to stick it in here. So let's see how good you are at that. I did it, and I got 3.679449474. And what I'm looking for is accuracy, right? We started at 4 up here. We started at 4. We went to 3.7. Well, 3.67 is pretty close, right? We rounded it's 3.7. But notice we have 3.679. And here we have 3.679. So I know I'm accurate to this root to at least 3 places. I'm going to do A5 now. A5 is this number that we just got for A4 minus the function evaluated at A4 all over the derivative at A4. So now you're going to take this number and stick it here as itself inside the function and then inside the derivative and do the math. So you can see how this quickly becomes very tedious, but in the grand scheme of things, if we had no idea what this root was, all we would have to do is just some serious algebra, because when I stick it into the function, worst case scenario is I'm squaring this number, which is just a lot of multiplication. I'm multiplying it by 2, and then I'm subtracting 6 times that number and subtracting 5, and then dividing it by 4 times that number minus 6. And when I do this for the fifth one, see how well you can do in your calculator. I get 3.6794. 49472. So now if you notice, this goes all the way out to almost the last digit. And when I do the sixth one, it's going to be the fifth number minus the function evaluated at the fifth number all over the derivative at the fifth number. And when I do this, I get the exact same value as the fifth. Now it's really not, but as far as my calculator can carry out to digits, it is. So notice, these are the same, and this is where we're going to stop. So however accurate, we can stop now. You want to be, if we wanted to be accurate out to 2 places after the decimal, then we had nothing in common here. We had just the first digit. If I wanted to go 2 places after the decimal, I could have stopped at my 4th iterate because they were accurate out to 3 places. And then right away we went from 3 places to 7 places. And then 7 places out to 8, but we don't know how much further because my calculator doesn't go much farther. So therefore, we estimate the root of f of x equals 2x squared, right? I already forgot what my function was. Minus 6x minus 5 in the interval from 3 to 5 is about 3.67944947 Right. So again, you could just pop this in your calculator and have your calculator find the root. But the process is a calculus process. You should know it, and this would be a good test question that says, show how you can find the root using Newton's method. All right, let's try another one. And I'll give you a trick on how to find these numbers a lot quicker than that. All right, use Newton's method to approximate the root of f of x equals 3x to the 4th minus 5x squared minus 6x minus 5 in the interval from 1 to 2. We're going to make an initial guess. They're not going to give you an interval if there's not a root in it. So I'm going to make my initial guess. I'm going to just go right dab, slap dab in the middle. I'm going to let it be 1.5. So my function f of x is equal to 3x to the 4th minus 5x squared minus 6x minus 5. And then I need the derivative of my function, which is 12x cubed minus 10x minus 6. So A2 is going to be A1, 1.5, minus f of 1.5, all over f prime of 1.5. All right, now that I made you do the dirty work, let me show you a trick on your calculator, all right? Because immediately this is going to come out to be a pretty horrible number, and there's lots of places to stick x's in. So here you have to be really careful that you do this carefully and you put parentheses in the right places. So let's see if I can get this in a good window here, right? All right, so what I do, I'm gonna clear my function. Right. I put my initial guess in, 1.5, and I hit enter. So now 1.5 is in my calculator's memory as the previous answer. Let's see if you can, hopefully you can see that. Yeah, looks good. Okay, now what I'm going to do, it's really important that you don't type 1.5 again, okay? Because we're going to use 1.5 as my calculator's answer in its memory. So I'm going to replace everything here with answer. And this is important because it's going to help us down the line. So I'm going to use, if you look right above your negative button right here, it says answer. It's hard to see mine because of the color of my calculator, but right above negative, it says answer. So I'm going to do second answer because I'm going to take my answer and I'm going to subtract from my answer this function evaluated at my answer. So parentheses are essential. Right, so I'm going to do a parenthesis and I'm going to do 3 times answer. So use that answer key, and everywhere where you really want to put a 1.5, you're going to put answer instead. Then I'm going to raise that to the 4th power. Minus 5 times second answer, raise that to the 2nd power, right? Minus 6 times second answer, minus 5. That's my whole numerator, so I'm going to close the parenthesis, and then I'm going to divide by, essential to use parentheses, my whole denominator, which is 12 second answer cubed minus 10 times second answer minus 6. I'm going to close that. Right now when I hit enter, it's going to give me this answer right here. So I'm going to hit enter, and the next value is 2.01602, blah, blah, blah. So I'm going to approximate this. This is going to be 2.01602561. So it did jump outside my interval, but that's okay. If you notice, it's going to swing back in. Right? Don't touch anything on your calculator, right? Because now this is A2. Now this is now stored in the memory of my calculator. So if I use the answer key in another function, it's now going to be thinking of this as my previous answer. So for A3, right, previously we took A2, subtracted f of A2, and divided by f prime of A2. But I have this whole thing already stored in its memory here, and I have this new answer. So at this point, so I hit enter, this gave me the number A2, the second guess at the root of this 4th degree polynomial in the interval from 1, 2. Now I'm going to hit, if you look on the bottom right hand corner, you have an enter button. If I hit second enter, it's going to reprint everything we just did. And notice the answer stayed in there, but now instead of using 1.5, it's going to use 2.016. It's going to use this number. So it's going to do this work for us right here, where A2 is going to put A2 here. It's going to stick it into the function, and it's going to stick it into the derivative. So now I hit enter. It's going to give me the next iterate after I hit enter. So it's the next number is going to be, the next guess at the root is 1.847814782. So my first guess was 1.5. Then it threw me slightly outside of the interval and said, nah, 2.016 is a better estimate at the root. So we use this, and this whole combination of stuff right here is finding the tangent line at that point and looking for the y-intercept of that new tangent line. And that gives us our third iterate, which is 1.84. Now again, we're looking for similarities from one to the next. My fourth one is going to be the third one minus the function evaluated at the third one all over the derivative at the third one. Now it's in my calculator, we would have to take this and would have to stick it here, here, and here. But fortunately, that number is now stored in the memory of my calculator as the previous answer. I hit second enter. Whoops, nope, don't do that. Second enter, it takes that whole little formula function, which is this guy right here, and it's going to use as its answer the 1.84 number, and I hit enter. Oh look, we're at 1.81. Notice we're going to start looking similar. So the fourth iterate, I got to zoom back out now. The fourth iterate is going to be 1.812372372487. Right? So now we know we're accurate. It goes from 1.84 to 1.81. We're accurate to one place after the decimal. So I want to get more accurate, and I'm going to stop writing this. I'm just going to hit these buttons on my calculator. So if we were to take this fourth iterate, stick it back into that template, I go second enter and hit enter. It's now going to give me the fifth guess of 1.81089426. So notice we're starting to see more similarities between the outputs. And I'm going to do it again. I'm going to find a sixth estimate of the root. I hit second enter and then enter. Oh wow, look at that. We're at 1.81089.176. So now we're accurate out to, right? We're accurate out to 5 places after the decimal. So you stop whenever the directions tell you to stop. I'm going to keep going until it's exactly the same, and all it took was one more operation. And now we're exactly at 1.81089.176. And then from then on out, they should all repeat and be the same. So therefore, the estimated root of the function f of x equals 3x to the fourth minus 5x squared minus 6x minus 5 in the interval from 1 to 2 is approximately equal to 1.8108976. And I challenge you to put that back into the original function and see that it in fact equals 0. And I'm going to actually do that because look, I can use that answer button on my calculator. I can do 3 times answer to the 4th power minus 5 times answer squared minus 6 times answer minus 5. And when I do this, what do I get? 3e to the negative 12. So that's exponential notation. So that says we take the decimal point to the right of 3. We move it 12 places to the left. So that is 0.000 with 11 zeros, then a 3. That's pretty close to 0. All right. So here for this original problem, we don't have a formula for a 4th degree polynomial like the quadratic formula. Ooh, I'm way out here. Okay. So we have to have other ways to find roots, and this is one of them. All right, let's try this problem. Use Newton's method to estimate the cube root of 50. Well, 50 has a cube root. It's not a very nice number, but we're going to approximate it. Right? How can we use Newton's method to approximate this? Well, finding the cube root of 50 is equivalent to solving this equation. X equals the cube root of 50, right? Which is the same thing as saying x cubed equals 50, right? If we raise both sides to the 3rd power, which is the same thing as saying x cubed minus 50 equals 0. So this is really, we can find the cube root of 50 by thinking of it as a root finding problem. We're looking for the root of x cubed minus 50. This is my function f of x, right? We're looking for the root of this equation. Okay. So we can use Newton's method. We're going to use Newton's method to do this. So my function f of x is equal to x cubed minus 50. F prime of x is equal to 3x squared. Right. Initial guess. Any idea what the cube root of 50 is? Well, notice. How would you guess this? Well, 3 cubed is 27. 4 cubed is 64. Right? So, the cube root must be in here somewhere between 3 and 4. Between 3 and 4. Because if we cube 3, we get 27. If we cubed, we're below the point we're looking for. If we cube 4, we're too high. So we're looking for a number between 3 and 4. I'm just going to go with the safety smack dab in the middle. I'm going to say 3.5 is the cube root of 50. All right? So A1 is going to be 3.5. A2 is going to be A1 minus f of A1 all over f prime of A1, right? Which I'm just going to write this out. You don't typically have to do this, but it's going to be f of 3.5 all over f prime of 3.5. So back in the old days when we were trying to estimate like something like the cube root of 50, and we didn't have a calculator to do this for us, I could take 3.5 and cube it and subtract 50 just by using lots of algebra. I could do 3 times 3.5 squared and get this output, and then I could do long division, and that would give me the next iterate A2. But again, we're going to save ourselves that headache because my guess is if you've made it this far in calculus, you can do the algebra. We just want to sort of understand the process. So I'm going to clear my calculator, and I'm going to do 3.5 as my answer. So that's my initial guess. Now remember, we're going to do second answer minus, well, the function evaluated at the answer. Let's go back up here. Here's my functions right here. So it's going to be the function divided by the answer. So I'm going to put the whole numerator. It's going to be second answer cubed minus 50. You don't want to use that number 3.5 at all. You want to call it answer, because then it will let us keep doing the process without having to retype everything. So answer cubed minus 50, all divided by parenthesis 3 answer squared. So my first guess was 3.5, and this should give me a better guess, 3.69. So I'm going to write that one down. 3.69, 3877551. Right now we're going to repeat the process with this number, and we're going to find a third best guess. And a third best guess is, we go second enter, and my calculator is going to do all this again. It's going to take the previous answer, and from that it's going to subtract the function evaluated at the previous answer minus the derivative at the previous answer. I'm going to hit enter. And notice I'm already getting pretty close, 3.68405772. Now what we're doing, we could all do with algebra. We're just choosing to use our calculator as a time saver. So I'm going to do second enter, and now it's going to use that 3.68 number. Oh, I'm getting very, very close. 3.6840. So I'm accurate out to 4 places, 31499. I'm going to do second enter. I'll use that previous number, and there we go. We match right up. It only took 5 shots. So if we were doing algebra out, and doing this all by hand, it would take us a while, but with the guess like 3.5, we were pretty close. The actual answer is only 3.68. So the cube root of 50, estimating it using Newton's method, is 3.68403149. All right, have fun with this. Zoom in if you have questions or if you need some help using your calculator. See ya.